Hi everyone, welcome to the next video in the series. This video is going to be mostly a review of some topics from algebra and pre-calculus on inverses. We're going to talk about inverse functions, horizontal line test, domain, finding the inverse of a function, and this is finding the derivative of an inverse function, but that will be in the next video. So here are some notes. I got these directly from the chapter, and this talks about the definition of an inverse function. And what it says here, and I'm going to talk about this more, is this composition function, right? So they're saying that the function g is the inverse function of f. So if you take the composite function f of g of x, it's going to be x for every x in the domain of g. And then g of f of x is also going to be x for every x in the domain of f. And function g is denoted here, f to the negative 1. Now that's not to a power. That's actually, so what it would say here is g of x would be equal to f inverse. That's how you say that. And so it looks like this. So when it talks about f of g of x, it means f of f inverse of x. And then when it says the other way, f inverse f of x. And then they both equal x. That's how you know that they're an inverse of each other. So here's some important observations. It talks here about the inverse functions. If g is the inverse of f, then f is the inverse of g. So it is a one-to-one relationship there. And it says if the domain of f inverse is equal to the range of f, and the range is equal to the domain. And we saw this earlier on one of our assignments. A function need not have an inverse function, but when it does, the inverse function is unique. So, I mean, you can do the process of finding an inverse, but the inverse doesn't necessarily become a function either. So when it says an inverse function, it will always have an inverse, but the inverse is not always a function. So you remember from algebra to pre-calculus that the existence of an inverse function can be determined from a graph. So as you see here, this is the function right here. This is f of x. And you can see that a horizontal line going through this intersects it in at least 2 points. And so it fails the horizontal line test. Remember, vertical line test just says it's a function, and of course it passes that. But the inverse of this function is not a function because it fails the horizontal line test. And so that's what it says, and this is from the book, so you can always go back to the book and look at that. Another thing that it talks about here is that a function is, you see this word, strictly monotonic, when it's either increasing on its entire domain or decreasing on its entire domain. So when you look at this one, you can see it's increasing and then changing to decreasing. This one is not monotonic. But if you had a cubic function that was always increasing, or tangent even, this one would be strictly monotonic. So make sure that you have that term down in your notes, strictly monotonic. It's either increasing over the entire domain or decreasing on its entire domain so that it never changes like this one right here. All right, and then it says the existence of an inverse function. It says a function has an inverse if and only if it is one-to-one. Now a biconditional statement, if and only if, means that you could read it forward or backwards. You could say a function has an inverse if it's one-to-one, or a function is one-to-one if it has an inverse. And one-to-one means that for every x there's a unique y. You can see here that for a and for b, it does not, they have the same y. It's not unique. But for this function right here, every x has a different y. That's one-to-one. And then here it says if f is strictly monotonic on its entire domain, then it is one-to-one and therefore has an inverse function. Now, they all have inverses, not all have functions. Okay, so if this is strictly monotonic, it passes the horizontal line test. it is 1 to 1. For every x, there's a unique y, and therefore has an inverse. So here are some guidelines for finding the inverse function. It says determine the theorem to determine whether it has an inverse function. Solve for x as a function of y, right? Interchange x and y, and then the resulting equation will be f inverse of x. Define the domain as the range of f, and verify that the composite functions equal x. All right, so let's do that. For this function, find the inverse function of f of x equals 2x minus 3. All right, so that's my f of x. To find f inverse, I'm going to substitute a y for f of x. Then I'm going to switch x and y and solve. All right, so the first thing I'm going to do is square both sides. I'm going to add 3 and divide by 2, and that's going to be f inverse of x. Okay, so the domain of this function right here of f of x is 2x minus 3 is greater than 0. So 2x is greater than 3, x is greater than 3 halves. All right, so the range of this, since this is the domain of the f function, it will be the range of the inverse function. That's as high as it gets, no matter how many x, what value x is. All right, so the range of f, right, is the domain of f inverse. All right, so we've done that. That's 4. And then the last thing is to do the composite function. So the first thing I'm going to do is f of f prime of x. And so that's going to be, here's f. So I've got the square root of 2 times, and then I'm going to put x squared plus 3 over 2 minus 3. All right. And then you can see that this and this cancel. This and this cancel. The square root of x squared is x. So this equals x. All right, I have to verify the other. So I have f prime of f of x. And so I'm going to start with my outer function this time, the inverse function. So I do that, plus 3, and then I put the function inside there, 2x minus 3. So the square root of something squared is just 2x minus 3 plus 3 over 2. So that's 0. That counts as 1, and that's equal to x. So that's verifying that both of those composite functions equal x. So this is indeed an inverse function. So another thing to remember about inverses is that the graphs of inverses are negative, are reflections of the function over the line y equals x. So for instance, if I had this graph right here, which is the negative half of the square root, so negative, of the x squared is just 1/2 of the x squared from negative infinity to 0. Then if I were going to find the inverse of this function, right, I would have this function and I would switch the x and the y coordinate. So if I had something like this, and this would be over and up, so this would be over and down. And so what you end up getting then is a reflection of that over the line y equals x. And so your f and your f inverse, the result of that is that f of x, right, equals y, and f inverse of y equals x. So in other words, you are switching x and y. So for instance, if you have f of 0 equals 1, then you would have f inverse of 1 would equal 0. This would be the point 0, 1. This would be the point 1, 0. And so this function notation, when you write it like this, it's really important, especially when they begin to substitute then g of x for f inverse. You need to be able to recognize that f of 0 equals 1. F of 0 equals 1 is this point. And then when you go to find a point on the inverse graph, then you are going to switch x and y. Okay, so the last type of problem that we want to look at in this video is determining if a function is strictly monotonic. And remember that the definition of strictly monotonic is that it's a function that's either always increasing or always decreasing. And therefore one-to-one, meaning that for every x there's a unique y. Monotonic means increasing, right? So if we think about this in terms of the slopes of the tangent lines of an increasing function, it means that all the slopes on that function are going to be positive. And if the function is decreasing, then the tangent lines are always going to be negative. So what that means for us is that if we take the derivative of a function and we analyze it for all values of x in its domain, so over the entire domain, no matter what we put in, positive or negative, if we take it to the fourth power, it will always be positive. If we take it to the second power, it will always be positive. So therefore, we find that 5x to the fourth plus 6x squared is always going to be greater than or equal to 0. And therefore, it is always, f is going to be always increasing. So that makes it strictly monotonic, right? And therefore, it has an inverse function. F of x has an inverse function. So let's look at a slightly different one. If we talk about the cosine function, if you'll remember what a cosine function looks like, right? If we do this, a cosine function oscillates. Now what we notice here is this does not have, this is an unrestricted domain. And as such, it clearly does not pass the horizontal line test. So I know pretty much before taking the derivative that this one is not going to be monotonic if it's unrestricted. Now, if I restricted the domain from, say, here to here, then you can see that that part of the function would actually be, it's a restricted, so just to that part of the domain, and it would pass the horizontal line test. And therefore, that part of the function would be strictly monotonic. But since this is unrestricted, and you can see that if you take the derivative of this function, you're going to end up with a sine function, the negative sine function, 3/2 sine x, 3x over 2, sorry. And you can see that even if it's sine, it's still going to not be strictly increasing or decreasing. So it is not strictly monotonic, not increasing or decreasing over its entire domain. And so the inverse is not a function. So it has an inverse, but the inverse is not a function. Okay? So I've done parts of the lesson for tomorrow's homework, and then a little bit. These last two problems are going to be on the next homework. So be sure that you've taken really good notes, and I will see you in class.